All right, we're moving on to chapter 8, and this is on confidence intervals. So we've seen these notes before, but let's just go through it again. So let's just recall. We've been talking about inferential statistics, which is all we're saying is that we're using sample data to make inferences about the population. So we've seen this picture multiple times before. We have the population with these true population parameters. We take samples, we calculate sample statistics. We use these sample statistics to make inferences about the population parameters. Okay, so this is just repeating what I just said. We're interested in the population parameters, such as mu, sigma squared. We use sample statistics, such as sample mean, x bar, sample standard variance, s squared. And we're using these to estimate the population parameters. And we called this process point estimation. We called this point estimation because it's a single point. X bar is a single point for mu. S squared is a single point for sigma squared. But we're now moving on to something called interval estimation. So instead of just having one point, we want to create a range of plausible values for these population parameters. So to do that, this chapter is about what we call confidence intervals. So confidence intervals will establish a range of plausible values for the population parameter. Okay, so that's what we're doing here. So let me actually delete some of this. So let's represent this. So we have been starting with some estimate. Let's say x bar. It's a single point, right? There's just this one value. It's a number, x bar. But what we're going to do now is we're going to create a range of values from here to here. So I'm going to take my estimate x bar and subtract off what we call a margin of error. And then I'm also going to take x bar and I'm going to add a margin of error. Now when we do this, we're creating our entire interval, our confidence interval. So this whole range we're going to call our confidence interval. And this is what we're saying whenever I say a range of plausible values for the mean is going to be x bar plus or minus a margin of error. So let's define a couple things. Let's start with confidence level. So confidence level. So this is just the percent of intervals that I expect to include the true parameter. So if I take samples over and over again, I create these confidence intervals for each of these samples, I would expect whatever my confidence level, that percent of my intervals to contain the true parameter. And we're going to define it as 100 times 1 minus alpha. So alpha is just like our error rate. It's the percentage of time we're going to be incorrect, or the percentage of time the interval does not contain mu. So alpha will just be something that we decide before we start a problem, or it'll be given to us. So we take our error rate, 1 minus that will be our confidence level. So these are things that as scientists, this is what we get to decide on. We're going to choose before we start doing any research. This is our confidence level. This is our alpha level. So let's just take a couple examples. Let's say alpha is 0.05. So we're willing to be incorrect about 5% of the time. Well, then that means that 1 minus 0.05, so 1 minus 0.05 would be 0.95. You multiply it by 100, and you get 95%. So if alpha is 0.05, then we have 95% confidence. Similarly, let's say alpha was 0.01. Well, then our confidence would be 1 minus 0.01 is 0.99, multiply it by 100, and that gives us 99% confidence. So alpha and our confidence will add up to 1. Okay, so now we're ready to finally create our formal definition for the confidence interval. So a confidence interval for the mean, for mu. So what we're going to say is that it is a point estimate plus or minus some margin of error. So in other words, our point estimate for mu, we've done this multiple times before. Our point estimate for mu is x bar, and we're going to add and subtract this margin of error. So notice that we've got a couple components here. So z alpha, so alpha will be determined before we start a problem. It'll be the proportion of time we're willing to be incorrect. And we're going to look up the corresponding z value. So z values come from our tables. So it's going to be what we call a critical value. Z is our critical value. And then sigma over square root of n, this is what we call the standard error. And recall, we use sigma over square root of n because that was our standard deviation for our sampling distribution, or our standard deviation for x bar, which is why we're using sigma over root n there. So once we do that, we're going to plug our values into this formula, and we're going to get an interval. And then we need to interpret it. And we're going to say, so say I have an interval. I will say I am however percent confident. So that could be 95. I'm 95% confident that mu, the population parameter we're interested in, is in the interval from the lower bound to the upper bound. The lower and upper bounds just come from this interval. That's what we're going to be calculating. So to do that, let's just have a quick note on notation. So let's just define z alpha. So z alpha is just the value of z such that the area to the right is equal to alpha. So let's just look at this plot. So this is our normal curve. It's centered on 0 because it's z. And I'm just saying z alpha is just going to be that value such that alpha percent is to the right of it, represented by the orange highlighting. So the area of the orange highlighting is equal to alpha. Z alpha is just the corresponding z value such that we have alpha percent to the right of it. So if we did some examples, if you looked up z 0.05, so if we were to say this area is 0.05, well then you would find that the z value would be 1.645. Again, let's say we wanted this alpha to be 0.01, 0.01. Well then, we would look up the z value, z 0.01, and if we did that, we would see that that value is 2.326. So that would mean that this z value here is 2.326. So that's what we mean by that. And with confidence intervals, we're going to be pretty consistent with what we use. For example, we'll do a lot of 95% confidence intervals. And when we do that, we'll use the value 1.96. Because recall that our formula for confidence intervals is actually z alpha over 2, not just alpha. The reason for that is that we need an upper and a lower bound. So that means we could be incorrect on the low end, and it means we could be incorrect on the high end. So that's why we're always going to divide by alpha over 2. So let's say alpha was equal to 0.05, well then we would have 95% confidence. And so we would need alpha over 2, so that would be 0.025, and z 0.025 would be 1.96. Z 0.025 is 1.96. So in the context of the confidence intervals, the z alpha, or really our z alpha over 2, determines how confident we want to be. And like I said, we get to decide that before we decide or move forward with any analysis. Okay, so that's our introduction to confidence intervals. It might seem weird, a lot of these concepts might seem a little odd, but in the next video, we'll do some examples, and I think it will be pretty clear. It's pretty mechanical. and we'll get through it.